In section 6.1, we're going to explain the basic behaviors of waves. We're going to describe the wave nature of light. We're going to learn some equations for relating frequency, wavelength, and energy of a wave. We're going to distinguish between line and continuous emission spectra. And then we're going to describe the particle nature of light. First off, what is electromagnetic energy? We've really been wondering this for a long time. Our very first ideas around this came from Isaac Newton, where he did some experiments and decided that white light consisted of individual colors of rainbows combined together. Anybody who has seen the classic experiment with like a prism, you shoot white light into it and you see a rainbow come out, you can see where he came up with this idea. And then he started to theorize that light was composed of streams of extremely tiny particles traveling at very high speeds. After that, we had some early experiments. Thomas Young started passing light through very narrow slits and noticing these interference patterns that was happening. This kind of made him kind of start to question Newton's ideas, because while we didn't have any good math to decide why these interference patterns would happen with particles, it does fit very nicely into the theory we had about waves and how they propagate. After that, James Maxwell, he started to theorize that what light was actually only a small part of a vast spectrum of electromagnetic waves, that we were only really looking at a small part of a greater whole. All of these observations started to lead to something we call the wave-particle duality of light, that it behaves both as a wave and a particle. We talked a little bit about interference patterns. I'm going to use some language that we haven't really defined yet, but I want you to get an idea of what this is. Interference patterns arise when light passes through these narrow slits. What can happen is that the peak from one wave corresponds with the trough of another. They cancel each other out and we get destructive interference. These are the darker parts of the interference pattern. Another option is that two troughs or two peaks come together and they add to each other. We get constructive interference, and we actually wind up with a spot that's brighter than even the initial lights were. Again, these are only really explained by the wave properties of light. And here we can picture an interference pattern. One of the first things you might be questioning is, why do we even really care about this? And really, the interaction between light and matter is used a lot to really analyze matter and to learn more about it. A lot of analytical techniques are based on this. Here is a picture I think that really illustrates how we can do this. This is a picture of the Crab Nebula. And we actually know that the light emitted by this nebula is due to the elemental composition within the nebula. So sulfur cations produce those green filaments that you see, and the red filaments are produced by oxygen cations. So by analyzing the light coming off the nebula, we get an idea of what its elemental composition is. So let's jump into this. Waves. A wave is an oscillation or periodic movement that can transport energy from one point in space to another. We kind of have an idea of what a wave is. We've seen waves before, but this is really a little bit more of a generalized definition than maybe we're used to. We can think of waves as maybe like you play jump rope. You shake the end of the rope, you see it kind of propagate through the rope. You drop a pebble into a pond and waves ripple across the surface. And even ones that we experience but can't really see, like the expansion of air that accompanies lightning, that thunder, that is a wave that is propagating out from the lightning strike. But in any of these cases, kinetic energy is transferred through matter, whether it be the rope, the water, or the air, while the matter remains essentially in place. So the speed of light. So waves are not just restricted to matter. In our previous examples, we actually have electromagnetic waves. And these consist of an electric field oscillating in step with a perpendicular magnetic field, both of which are perpendicular to the direction of travel. That is a big statement that would be covered a little bit more in a Phys 2 course, electricity and magnetism. We're not really going to get into that too much here, but we're going to talk a little bit more about how electromagnetic waves interact with matter. And the real thing that you need to have is a takeaway that there is a set speed of light as it travels through a vacuum. All light, electromagnetic radiation, regardless of its other properties, is going to travel at 2.998 times 10 to the 8 meters per second through a vacuum. How do we characterize these waves? So we've talked about a spectrum. They're all different, right? So there's different points in this spectrum. How are we going to quantify that? Well, we have three descriptors right here. We have the wavelength. This is the distance between two consecutive peaks or troughs in a wave. We have the frequency. This is the number of successive wavelengths that pass a given point in a unit of time, because again, this is propagating. It's moving through some medium, right? And then we have the amplitude, 1/2 the distance between the peaks and the trough, or essentially how high are the waves. What are our units for frequency? Frequency is usually described using reciprocal seconds, per seconds, and this unit is called a hertz. So it's important for you guys to realize that when you see this Hz hertz, that unit is synonymous with 1/2. The hertz is a really small unit, so you'll often see it in pretty high multiples. So you have the megahertz or 1 million hertz, or the gigahertz, 1 billion hertz are often used. So how can we relate these together? The product of a wave's wavelength and its frequency, which we're going to describe as lambda times nu, those are Greek letters, is the speed of the wave. So we have this relationship here where we have c, the speed of the wave, is always going to be equal to this constant and is equal to lambda times nu. Again, lambda is in units of meters and nu is in units of 1/seconds, and so we wind up getting this speed here of meters per second. Wavelength and frequency are inversely proportional, which means that as the wavelength increases, the frequency decreases, and vice versa. So let's see if we can kind of picture this a little bit. So here I have a distance traveled in 1 second. Okay, you can see here that a wavelength is from one peak to another. All right. So in this distance, we have traveled 1, 2, 3 wavelengths. So our frequency is 3 cycles per second, or 3 hertz. Here we are traveling 1, 2, 3, 4, 5, 6 wavelengths across in 1 second, and we now get 6 cycles per second, or 6 hertz. And you can see that as the frequency went up from 3 to 6, the wavelength went down. This wavelength would actually be half of what this wavelength, lambda 1, would be. And again, here we can see that after 12 cycles, the wavelength is even smaller, and we're getting through more and more of them in that 1 second time frame. Picturing amplitude, if you kind of thought of a line that went straight through the middle of this wave, the distance from that center point up to the highest peak or the lowest trough is going to be our amplitude. And here we have a lower amplitude. You can see that's kind of a squashed down wave. If the wave was even higher, we would have a higher amplitude. The electromagnetic spectrum is the range of all types of electromagnetic radiation. Visible light makes up only a small portion of that electromagnetic spectrum, and each of the various colors of visible light has a specific frequency and wavelength associated with it. So let's see if we can kind of picture that. So over here on the far left side of our electromagnetic spectrum, we have the highest frequency, lowest wavelength, highest energy types of electromagnetic radiation. That goes all the way up to gamma rays, which are very, very powerful rays. Some of our examples of that would be like cosmic rays. These are like cosmic radiation left over from the Great Big Bang Theory. The PET scan that's used in medicine uses gamma waves to essentially irradiate your insides to get images. Then we have X-rays. We're most familiar with these as a way of imaging bones, right? Because the X-rays can pass through our flesh, but they don't quite have the energy to pass through our bones, and we can do some imaging doing that. Then you have ultraviolet rays. These are used in a lot of things. Here they have the example of dental curing. There's also where they use ultraviolet radiation to cure like glues and plastics and stuff like that. And this is also the type of radiation that's going to give you like a sunburn from the sun. Then we have a very small portion here. It contains all of the visible light that we see. Okay. Then we have infrared radiation. We've used these for night vision and remotes and stuff. This radiation is most associated with like heat signatures and heat giving off infrared radiation. Then we start to get into microwave technologies, and these are used in things like wireless data signals, the data that goes to your phone and stuff, your cell phones, and they also power microwave ovens. And then we have this vast region of radio frequencies that are used to transmit both images and sound that we've been using for many, many years. So how do we interconvert between wavelength and frequency? We saw that they were related. We developed a thing. Let's do a little example here. We have a sodium street light that gives off yellow light that has a wavelength of 589 nanometers. What is the frequency of this light? So we rearranged the equation we had before to see that the frequency is going to be equal to the speed of the light divided by the wavelength. We know the speed of light. That's that 2.998 number. We have the wavelength in 589 nanometers. We do have our speed of light in units of meters per second, and we have this in nanometers. So we're going to have to make a conversion here. We need this to be in meters. So we make our conversion here, and we wind up getting 5.09 times 10 to the 14th reciprocal seconds. Here's an example where we can see that radio waves are everywhere, that we use them to send signals. These can be getting more and more sophisticated. We use them now for over-the-air TV broadcast. We use them for, more traditional things like ham radio, CB radio and stuff. But more and more, we're relying on this for data transmission and digital signals, like the new 5G that's coming out for your phone. How does it work? So, if this was the signal that I was trying to send, just this sine wave, right? I have two kinds of modulation that are typically used. You have AM, amplitude modulation, or you have FM, frequency modulation. So, how do these two work? So if I start off here, and I say, okay, I want my signal to increase to here, in AM modulation, I'm going to make the amplitude go up. So the higher the amplitude, the higher this wave goes. The lower the wave goes, the lower the amplitude is going to go on my signal that I'm sending, until I can reconstruct this signal based on the amplitude. With frequency modulation, what I'm doing is changing the frequency. So as the signal goes up and I want to have a higher signal, I increase the frequency. As the signal goes down, I decrease the frequency and then back up again over here. Both of these have their upsides and downsides, and that's why we still have both AM and FM radio. So not all waves are traveling waves. Not all of them go anywhere. They don't move through the thing. These waves are known as standing waves. And standing waves, really, they play an important role in our understanding of electronic structure because they're the first time that you start to see quantization. And basically what happens is if you have a standing wave, the standing waves can't just be any number of waves between 2 points. It actually has to be what they call half integers, or n times 1/2 wavelengths between the two endpoints. So this only leads to discrete values that are possible. And we can even have a special case of the harmonic waves in which some points between the two endpoints are not in motion. These are known as nodes. And we're going to see a little later that at the quantum level, the very small level that atoms and electrons are working at, they also have quantized energies, and that these nodes start to appear in the way that electrons move. So let's see if we can picture this standing wave first. So I said that it was half integers of the wavelength. So if a wavelength is it going up and then back down again, we can see that this first top one here is actually only half a wavelength. So this is only a up and none of the down, right? Here we have 2 halves or 1 full wavelength. So we get the up, we get the down, it comes back to its first point, and in the center here we have this point that isn't moving. This is our node, right? While this is wiggling up and down, this guy stays stationary right there. Here we have 3 halves, so we're going to have 1/2 of a wavelength, the other half of a wavelength, and the third half of that wavelength. When we now have 2 nodes, and so on and so forth, each time adding a node and another half of a wavelength. This is not restricted to the one-dimensional example that we just had. This could also happen in 2 dimensions, or even we'll later see 3 dimensions. And one way of picturing that is to look at something that's like vibrating. So here they put like kind of gravel on top of these guys here, and then they wiggle it, and they can therefore create standing waves, which produce these patterns on the top with the gravel, where you can see those are where the nodes are forming. Black body radiation. So I'm going to mysteriously state that sunlight consists of a range of broadly distributed wavelengths that form a continuous spectrum. So we have a continuous spectrum coming from sunlight. A black body is a convenient, ideal emitter that approximates the behavior of many materials when heated. So if the sun is producing light from being heated, maybe we can kind of use the idea of the black body to model that. One good approximation of a black body that can be used to observe is the idea of like a metal oven. So what kind of electromagnetic radiation are we going to see when we heat up the inside of an oven? And then, so we have the problem with black body radiation that we have something called the ultraviolet catastrophe. The maxima in the black body curves, lambda max, shift to shorter wavelengths as temperatures increase. theoretical expressions as functions of temperature fit the observed experimental blackbody curves at longer wavelengths, but there is a significant discrepancy at shorter wavelengths, and this became the ultraviolet catastrophe. So let's see if we can picture this. So what we can see here is that as the temperature of a black body goes up, the largest lambda max, where you're seeing the highest intensity of radiation, gets to be these shorter and shorter wavelengths, and it gets to be more and more intense, right? Where here it's producing visible light, here it's producing ultraviolet light, and here it's producing infrared light. Now, if we overlaid that, the temperature of, with a black body, the temperature of the sun versus the sunlight, you see really good agreement for all of the infrared radiation and stuff. But then right here, even in the visible, it seems okay, but then you see this wild discrepancy right around where you start to move over to ultraviolet light, where it no longer appropriately models. The black body doesn't really fit the data we have for sunlight. So something is happening right here where we no longer have a good model for what exactly is happening within the sun using just the black body theorem. So what is that? Well, around 1900, Max Planck derived a theoretical expression for blackbody radiation that fit the experimental observations exactly. Planck developed his theoretical treatment on the premises that atoms are composing the oven vibrate. So he's thinking about vibrating atoms here. The atoms vibrated at increasing frequencies or decreasing wavelengths as the temperature increased. So what Planck did that was so revolutionary is that he started to develop a theory that related the energy of these vibrating atoms to the frequency. And he said that the energy has to be equal to n, where n is 1, 2, 3, or 4 or something, times some constant, which is known as his Planck constant now. You can see down here it's 6.626 times 10 to the negative 34 joule seconds. So you take joule seconds, you multiply it by reciprocal seconds, you get joules, which is the energy unit we've seen before. And the idea that it can only have these discrete values of 1 or 2 of times that, or 3 times that, or 4 times that, that is quantization that we saw before with the standing waves. So what exactly happened to cause this UV breakdown? Well, out here where we had higher wavelengths, lower frequencies, we have less energy, right? And everything behaves really, really nicely. Then all of a sudden we start to get into this visible UV radiation. And what's happening is the electromagnetic waves at this point now have enough energy to start doing different things. They now are able to excite electrons, to cause atoms to do things other than just vibrate. And that leads to this kind of erratic behavior around it as as more and more modes of energy transmission are possible. So thinking that the atoms are just vibrating isn't going to work for these higher energy electromagnetic waves. This enters into the photoelectric effect. And it had been observed that electrons could be ejected from the surface of metal when hit with the right kind of light. So the frequency of this light has to be large enough, therefore they have to have enough energy to eject these electrons. And what was surprising to them is that this didn't rely on the brightness of the light, but instead to its frequency of the light. So they thought if I just keep hitting it with brighter and brighter light, I'll get more and more electricity out. That seems to make sense. But it wasn't the important thing to actually get the electrons to eject. So according to classical wave theory, a wave's energy depends on its intensity, which depends on its amplitude, not its frequency. And then enter Albert Einstein, who was able to resolve the paradox by incorporating Planck's work into his view of particles as a light, his particle theory of light. He actually won the Nobel Prize for that. A lot of people think Albert Einstein won the Nobel Prize for something different, but it was actually for this photoelectric effect that he was working on. So in order for this to work, though, and we've been talking about how light behaves as waves, light can't be a wave here. It actually has to be a particle. So we go from the idea with Isaac Newton of light being a particle to the work of Maxwell and Planck and others, where they're saying, no, this behaves as a wave. And then with Albert Einstein, we're now going back to the notion that light has to behave like a particle. This leads to this duality that light does both. So if we have these equations now that the energy is going to be equal to Planck's constant times the frequency, we can substitute in our idea that frequency is equal to the speed of light divided by lambda, and we now have a equation that's going to relate energy to wavelength as well. So, what is the photoelectric effect? So, electrons are injected when they're hit by photons having sufficient energy. The greater the frequency, the greater the kinetic energy imparted to the escaping electrons by the collision. Somehow, at a fundamental level, still not fully understood, light is both like a wave-like and particle-like. This is known as the wave-particle duality. So let's picture that for a second. So at 700 nanometers, we don't get any electrons off. All of a sudden, we hit some critical value, somewhere around 550 nanometers, and we start to see these electrons getting shot off, and they have their own velocity. And we can measure that. So let's say that at 550, we get 2.96 times 10 to the 5 meters per second electrons shooting off here. If we go even lower wavelength, higher frequency, higher energy, we see that these electrons start to shoot off quite a bit faster, 6.22 times 10 to the 5 meters per second. So let's do a little example where we're looking to calculate the energy from the wavelength. So when we see light from a neon sign, we are observing radiation from excited neon atoms. If this radiation has a wavelength of 640 nanometers, what is the energy of the photon emitted? All right, so we're going to use that equation we had before, where energy is equal to Planck's constant times the speed of light divided by lambda. We're going to remember that we need to convert our wavelength from nanometers to meters. We cancel all of our units, we get joules, and we see that this light has an energy of 3.10 times 10 to the negative 19 joules. So one thing to point out here is that we get this energy value in joules, and it was kind of tricky the way they asked the question. So they said, what is the energy of the photon emitted, right? So what we're really calculating here is that this is the energy per photon. And some other times when they're going to ask these questions, if you look in the homework, sometimes they're going to ask, what is the energy per photon? And they may even start to ask you, what is the energy of multiple photons? In which point you need to realize that that would just be some multiple of this energy. So there's a good example of this in the homework problems. It's just something to pay attention to, that It really depends on how they ask the question. So, continuous spectra. So, the scientists in the late 19th century, they were also struggling with something else. They were looking at light that was emitted from atoms and molecules. And they noticed that when solids, liquids, or condensed gases, gases at high pressure, relatively low temperatures and stuff, are heated sufficiently, they radiate excess energy as light. Okay? And when they were looking at this, they saw that this produced a continuous spectrum, so that there were photons of many different frequencies that were in a whole continuum. However, when they started to look at gases at low pressures, they started to see what they call line spectra, these discrete spectrums where only light of specific frequencies were emitted. And we can kind of picture that with like the neon signs. So you put different types of gases in these glass tubes, and then you go ahead and heat them and apply electricity to them, and they automatically glow with a specific color that is associated to a specific frequency that they're emitting. Each emission line consists of a single wavelength of light. This implies that the light emitted by a gas consists of a set of discrete energies. That's that quantization again. The origin of discrete spectra in atoms and molecules was extremely puzzling. Where is this coming from, right? Because it really didn't fit with their classic electromagnetic theory. Here we can picture those line spectra that are happening. On the top we have a continuous spectrum, and then down here you can see that if you did sodium you'd only get these frequencies, and if you did hydrogen you'd only get these ones. So what's happening is that there is quantization here, okay? If the mechanism that is causing photons to be emitted here is that photon is absorbed by hydrogen, right? And then that causes an electron to go to a higher state, all right? And then the electron falls back down. It's going to emit a photon that has a specific thing here. So if all the electrons in hydrogen could have any value, any energy state, then you would get the continuous. But if there were only some permissible energy states for the electrons in the hydrogen, then you wind up getting these discrete states. That again is an example of the quantization, and we're going to jump into that now with some of the theory behind it. In 1885, Johann Balmer was able to derive an empirical equation. So empirical meaning he looked at data and he found an equation that was going to fit that data. He didn't really have any good theory behind why it was true. The equation related the 4 visible wavelengths of light emitted by hydrogen to whole integers. So here he's able to say, well, the wavelengths that we're going to get out, or 1 over the wavelength that we're going to get out, is going to fit this. Okay, so I have some k value here, and if I start pumping in integers of 3, 4, 5, and 6, I'm going to get out the proper wavelengths that I see. Other discrete lines for hydrogen atoms were found in the UV and IR regions, and it wasn't really, and so this didn't really account for that. But a guy named Rydberg comes along, looks at Balmer's work, and he's able to develop an empirical formula that predicts all of the emission lines, where he now has his constant that he pumps in here, and using his constant he's able to have 2 different n values, where both of these n values are integers. One is always less than n1 is always less than n2, and we are able to now get all of the possible predicted hydrogen emission lines. In section 6.2, we're going to get into describing the Bohr model of the hydrogen atom, and we're going to use the Rydberg equation to calculate energies of light emitted or absorbed by hydrogen atoms. So let's think about what Niels Bohr did. So he eventually was able to come up with some explanation for the spectra of hydrogen. His work was able to convince scientists to abandon classical physics and spurred on the development of modern quantum mechanics. What did he say? He said that atoms consisted of tiny dense nuclei surrounded by lighter and even tinier electrons continually moving around the nucleus. So we've already kind of had this idea, right? This classical mechanical description of the atom is incomplete, since an electron moving in an elliptical orbit, so like in some sort of circle, like the moon moving around the Earth, it would be accelerating. And if it is accelerating and it does have a charge, well, an accelerating charge is going to emit electromagnetic radiation. That is something that we know from physics. If it's emitting radiation, then it's losing energy. If it's losing energy, then the orbit should get smaller and smaller until eventually it hits the nucleus, much like a satellite that's slowly coming closer and closer to the Earth until eventually it doesn't have a stable orbit anymore and it comes into our atmosphere and hits the planet, right? So he attempted to resolve this atomic paradox by ignoring classical electromagnetism's prediction that the orbiting electron and hydrogen would continuously emit light. So he said it's not going to shoot off light. Instead, what's going to happen is he's bringing in a lot of ideas from Planck's about quantization and the idea that the light consists of photons, and he starts to assume that the electron orbiting the nucleus would not normally emit any radiation. Rather, the electron emits or absorbs a photon if moved to a different orbit. So basically, he's saying that electrons have set orbits, and when they move between them, this is accompanied by the absorption or emission of a photon. The energy absorbed or emitted would reflect differences in the orbital energies according to this equation. So we have the change in energy is going to be equal to the final energy of the electron minus the initial energy of the electron. We already saw this with temperature and enthalpy. We were used to that kind of mathematical form. That's going to be equal to h times nu, like Planck said. Again, we can rewrite that in terms of wavelengths. And we're going to assume here that there are only discrete values for delta E, that there's only some delta E's that are permissible. And he came up with this expression for that, where he says that the energy value that are possible are all going to be some constant divided by n squared. They're always going to be negative in this scenario. And then he actually, instead of just saying, well, the k value is this, he started to develop an idea of what this k value, where it was coming from. So he had some basic fundamental constants such as the electron's mass, its charge, Planck's constant. These all comprise k. So he gave us some idea where that k value was coming from, as opposed to like Rydberg or Balmer. And it's also consistent with what we were seeing already. So if we look at delta k, or delta E, right? So if we take this E minus some other E, then we get an expression that looks like this. And if we rearrange that expression, we get something that looks like this. And if we look at k divided by hc, we say, well, that is actually Rydberg's equation. So this theory that gives us a little bit more insight into what is happening is consistent with what we already know to be true for the hydrogen atom. And this gave scientists the idea that maybe Bohr was onto something here. So I want you guys to start to picture what it is I'm saying here. So if you look here, this is the idea of the quantization of energy levels. So what we're saying is that there are permissible energy levels and there's nothing in between those energy levels. So you could have a bottom energy level here that is negative 2.18 times 10 to the negative 18, right? You could have a higher energy level here, a higher energy level here, on and on and on, but you can't have anything in between them. And this is going to be specific for different elements. So this, for instance, are the permissible energy levels that hydrogen can have. All right, so we've got some language to talk about here. So one fundamental idea that we have from the laws of physics is that matter is most stable when it has the lowest possible energy. So when an electron is in this lowest energy orbit, the atom is said to be in its ground state. If the atom receives energy from an outside source, it is possible for the electron to move to an orbit with a higher n value, and this is going to be an excited state. I think you guys have noticed that as I've been talking through this, I'm talking about them exciting electrons, and that is what happens when an electron moves from a lower energy state to a higher excited state. So what makes it move from one orbit to another? That is when an atom absorbs energy in the form of a photon. The electron moves from an orbit with lower n value to a higher n value. When an electron falls from an orbit with a higher n value to a lower n value, it's going to emit a photon. And since delta E can only be discrete values, the photon absorbed or emitted can only have a wavelength with a discrete value. It's not going to be continuous. This explained the line spectra that they started to see for the hydrogen atom. Let's see let's see if we can picture that. So what they're saying is if this is the ground state of the hydrogen atom, it can be excited to this first n equals 2 state. It could go past that to n equals 3 or n equals 4. Okay. Each of these is going to involve absorbing a photon of a different energy, a different frequency. If it was at any one of these states, say it was already at n equals 2, it can still go up to any of the other excited states. And it can also fall from one of these excited states down to each one. Each of these would be accompanied by the emission of a photon of a different frequency, each having different energy values. It doesn't have to fall all the way back down to the ground state either, and you can see that there's Okay, so let's use the Bohr model to perform a calculation on the absorption of a photon. So what is the energy in joules and the wavelength in meters of the line in the spectrum of hydrogen that represents the movement of an electron from Bohr orbit with n equals 4 to the orbit with n equals 6? In what part of the electromagnetic spectrum do we find this radiation? Okay, so in this case, the electron starts out with n equals 4. So N1, this first guy here, is going to be a 4. And it comes to rest in n equals 6. So N2 here is going to be 6. The difference in energy between the two states is given by this expression. And we got our K value here of 2.179 times 10 to the negative 18 joules. We'll plug him in there. Plugging in this value, we get the K value times 1 over 4 squared, 1/16th minus 1 over 6 squared, 1/36. We see that this is going to be a positive value, and we wind up getting 7.566 times 10 to the negative 20 joules. This energy difference is positive, indicating that the photon enters the system to excite the electron from the n equals 4 orbit up to the n equals 6 orbit. The wavelength of this photon, we're going to use this equation down here. So solving that for the wavelength lambda, we get h times c divided by that energy value. We input the Planck constant. We input the speed of light here. We see that the seconds are going to cancel here. The joules cancel here. And we wind up being in meters. And if we go back to the spectrum that we saw before, we would see that that wavelength corresponds to the infrared portion of the electromagnetic spectrum. So Bohr's model has some limitations. It was unable to extend his theory to the next simplest atom, helium, so it only works for hydrogen. It does not account for electron-electron interactions. It can't handle those types of interactions. And it was still based on classical mechanics notion of precise orbits. And we'll see exactly what precise orbits means in a little bit here. The Bohr model does introduce several important features of all models used to describe the distribution of electrons. So it was a move forward. The energies of the electrons in an atom are quantized. They're described by quantum numbers. Integers numbers having only specific allowed values and used to characterize the arrangements of electrons in an atom. An electron's energy increases with increasing distance from the nucleus. The discrete energies, lines, and the spectra of elements result from these quantized energies. Bohr won a Nobel Prize in Physics in 1922 for his contributions. It became clear to most physicists at the time that the classical theories that worked so well in the macroscopic world were fundamentally flawed and could not be extended down into the microscopic domains. A proper model of quantum mechanics was later developed that superseded the classical mechanics. Okay, in section 6.3, we're going to extend the concept of the wave-particle duality that was observed for electromagnetic radiation. We're going to understand the general idea of quantum mechanical descriptions of electrons in an atom, that it uses the notion of a three-dimensional wave function, or orbitals, that define the distribution of probability to find an electron in a particular part of space. And we're going to list and describe the traits of 4 quantum numbers that form the basis of completely specifying the state of an electron or atom. So, in the development of quantum theory, particles and waves are very different phenomena in the macroscopic realm, but they start to become almost the same thing in the quantum realm. This became clear in the 1920s that small pieces of matter follow a different set of rules than what we observe in the macroscopic world, and that the separation between waves and particles starts to break down when we get really small. Louis de Broglie, if an electromagnetic radiation can have particle-like character, can electrons and other submicroscopic particles exhibit wave-like behavior? In 1925, Louis de Broglie extended the wave-particle duality of light that Einstein used to solve the photoelectric effect paradox to materials particles. And he did that by defining something called the de Broglie wavelength. And the de Broglie wavelength is described mathematically here. It's Planck's constant divided by the mass of that particle times the velocity of that particle, or Planck's constant divided by the momentum, because mass times velocity is equal to momentum. In this wavelength, it's a characteristic of a particle, not actually electromagnetic radiation like we saw wavelengths be before. So Bohr had postulated that the electron is being a particle orbiting the nucleus in quantized orbits. De Broglie argued that Bohr's assumption of quantization can be explained if the electron is considered a circular standing wave. Only an integer number of wavelengths can fit exactly within the orbit. So if we look at that here, what he's saying is just like we saw for the standing waves, we're only going to have certain waves that are going to be able to fit. So if we only have half integer allowed waves and they have a specific wavelength, then there's only going to be certain distances away from the nucleus that are going to be able to have these stable waves where things start to come back and everything lines up nicely. For a circular orbit of radius r, the circumference is 2 pi r, and so de Broglie's conditions are that 2 pi r is going to equal n lambda, where n is equal to 1, 2, or 3. This means that the only permissible circumferences are multiples of the de Broglie wavelength. So de Broglie had given us some sense that electrons were behaving like waves, but we really didn't have great experimental evidence that this was true until Davison and Germer demonstrated experimentally that electrons can exhibit wavelength behavior. They showed that electrons traveling through a regular atomic pattern in a crystal produced an interference pattern. The interference pattern was very similar to those that we saw at the beginning of this talk for light. So if we picture what they were doing, they're shooting electrons at this split. It moves out and propagates as a wave, causing constructive and destructive interference, and then forms these regular patterns on a screen where they could view where the electrons had hit. So it appears that while electrons are small localized particles, their motion doesn't follow the equations of motions implied by classical mechanics. They don't work quite the same as like a baseball thrown or something like that. Instead, the wave, they travel as some kind of wave that we can describe using something called a wave equation. The next bit of information came from Werner Heisenberg. He determined that there is a fundamental limit to how accurately one can measure both a particle's position and its momentum simultaneously. Basically, he said that the more accurately we measure the momentum of a particle, the less accurately we can determine its position at that time, or vice versa. And this becomes known as Heisenberg's uncertainty principle. We can see that written out mathematically here. So if delta x is the uncertainty in the position and delta p is the uncertainty and the momentum, this always has to be higher than this h bar over 2, where h bar is it's Planck's constant divided by 2 pi. So this is just a number, a constant. So if you imagine here, if this has to equal a constant, as one of these goes to 0, say delta x goes to 0, delta p is going to approach infinity, and vice versa. As this uncertainty went to 0, this would get very, very large. So we can't know both of these at the same time, so the question becomes, how do we handle this? And the answer is we need to handle it statistically. And that's where we start to come in with Erwin Schrödinger. He extends de Broglie's work by incorporating the de Broglie relationship into a wave equation. This equation is now known as Schrödinger's equation. And what Schrödinger was able to actually figure out is he thought of the electron in terms of a three-dimensional stationary wave, or wave function. And he represented it by the Greek letter psi. And wave functions are functions that basically contain all of the information about any mechanical system, but really the only wave functions that we can fully understand are for the simplest cases, which would be for like single particles or small particle systems. A few years later, Max Born said that electrons are still particles, and so the waves represented by psi are not physical waves, but instead complex probability amplitudes. And what he means by complex here is like a complex number, like they contain imaginary numbers, i.e. like the square root of -1. And so to deal with that, right, to actually get to probabilities that we can work with, he started to look at the what they call the complex conjugate of the wave functions. And that's described here with these horizontal bars in this square. Basically, he takes the wave function, he multiplies it by its complex conjugate, and in doing so, he clears that imaginary portion, and he winds up getting out of that a not entirely intuitive probability distribution function. So this probability distribution function tells you where it's probable and likely that a electron be around the nucleus, and from this he can infer the electron density with respect to the nucleus in an atom. So you'll often see Schrodinger's equation written in this somewhat interesting form here that you actually have to get like pretty far in math to really understand, but what he's saying is that there is an operator. This is called a Hamiltonian. And what you can think about an operator as is it's just like a set of instructions. It's a set of instructions, mathematical instructions, add this, subtract that, multiply this, blah, 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 that you're going to perform on your wave function. And what you're going to get out of that is going to be the energy, so a constant value that is the energy, times the wave function. This is what is known as an Eigen Problem, or Eigen equation, where you perform a set of instructions on a function and that returns the same function with some sort of constant in front of it. And there's a whole bunch of set of rules for how you handle eigenfunctions. Schrodinger's work, as well as that of Heisenberg and many other scientists following in their footsteps, really laid the groundwork for what has become quantum mechanics. Some of the other great scientists that contributed to this work, there was Slater, who really spelled out some of the first functions that properly describe the orbitals of electrons. There was a guy named Hartree who developed a method for both calculating those orbitals and figuring out some of their energies. Fock worked on Hartree stuff to kind of perfect it a little bit more. Mulliken did a lot of really interesting work. He was working well up into like I believe the 60s on spin-spin coupling and a few other things, more complex electron-electron interactions. And there's still many people who are working in this field today. So what are our takeaways here? Electrons and atoms can exist only in discrete energy levels, but not between them. The energy of an electron in an atom is quantized. So that's really a restatement of that first bullet there. The energy can be equal only to certain specific values and can jump from one energy to another, but not transition smoothly or stay between these levels. The energy levels are labeled with an n value, where n is some integer. Generally speaking, the energy of an electron in an atom is greater for larger values of n, and that usually means that the electron is farther away from the nucleus. N is referred to as the principal quantum number or shell number. The principal quantum number defines the location of the energy level and is similar in concept in the Bohr model. So here you can see as n goes up, you're getting further and further away from the nucleus. So, atomic orbitals. The principal quantum number is one of three quantum numbers used to characterize an orbital. An atomic orbital is a general region in an atom that an electron is most probable to reside. An atom's orbital is distinct from an orbit. Okay, so we're talking about a generalized region here with an orbital. So this is like a three-dimensional object that has volume, which is different than an orbit, which is just a path, right? The quantum mechanical model specifies the probability of finding an electron in a three-dimensional space. All right. So the next quantum number that we need to be concerned about is the angular momentum quantum number. This is usually shown as a scripted L. It's an integer that defines the shape of the orbital. And L will take on values of integer values all the way up to n minus 1. So 0 through n minus 1. So if n is 1, L can only be 0. If n is 2, n minus 1 is 1, L has values of 0 and 1. If n was 3, n minus 1 would be 2, L could take on values of 0, 1, and 2. So a lot of times, instead of using these numbers for the L values, we instead use letters that represent the types of orbitals. For 0, there are the s orbitals, 1, there are the p orbitals, 2, there are the d orbitals, and 3, there are the f orbitals. Where they're getting these letters from, I really honestly have no idea. I've been looking for years and I've never found out. All right, radial nodes. So there are certain distances from the nucleus at which the probability density of finding an electron located in a particular orbit is 0. So these are what is known as the radial nodes. This is the three-dimensional version of what we saw before with the standing waves. The number of radial nodes is n minus L minus 1. So we have a couple of cases here. For instance, if n is equal to 3 and L is equal to 0, then there's going to be 3 minus 0 minus 1, 2 nodes. All of these cases apply to the s orbitals, which actually look like spheres. So let's picture what this means. So in the first case, we had 0 nodes, and we just get a sphere around the nucleus. In the second case, we have 1 node. So we have a larger sphere that is the 2s orbital, and the node is in the center where the 1s orbital is occupying largely, right? You can see that there is some overlap between this node. You can see that it's not perfect, right? There's some overlap between the two orbitals. It's not like the 1s orbital only exists where the node is, but they do roughly correspond to one another here. And similarly, here we have another shell on top of it with nodes that occur where the 2s and the 1s orbital is. And again, it's not perfect, but they roughly correspond with each other. There's some overlap between these, but not much. So what are these shapes of these different orbitals? They're actually pretty exotic. So the S subshell has a spherical shape. The P subshell looks kind of like a dumbbell. And the D and the F orbitals are a little bit more complex. So let's take a look at them here. Here we have our S orbital. Here we have our P orbitals. This could be arranged around the X, the Z, or the Y axis. These are all of our D orbitals here. You can see that there's actually one pretty exotic one here that doesn't quite follow the same clover shape as the others. And then down here we have our F orbitals with this guy here, which is also pretty crazy looking. It's got these little rings around it here, just like this guy. Those are called the torics. The next quantum number is the magnetic quantum number. So if an orbital has an angular momentum of L equal to 0, then this orbital can point in different directions. The magnetic quantum number ML specifies the orientation of the orbit, or L that isn't equal to 0, the orientation of the orbit in space. So the value of M sub L depends on the value of L. And it varies from negative L all the way up to positive L. Okay? And there are 2L plus 1 orbitals with the same L value. So one S orbital for L equals 0. There are 3 P orbitals for L equals 1. So if I put 1 in here, I'm going to get 3. Right? 2 times 1 plus 1 is 3. 5 for the D orbitals and 7 for the F orbitals. Okay, so what that really means is if we come back here, right? Here for the P's, for instance, we have L equals 1. We're going to go from negative L to positive L. So we start off at negative 1, and that's going to be your PX orbital. At 0, that's going to be your PZ orbital. And then at positive 1, you're going to have your PY orbital. I actually said that wrong. So at negative 1, you're going to have your PX orbital. At 0, you're going to have your PY orbital. And then the last one at, I don't know why the book arranged them this way. But at 1, you're going to have your PZ orbital. So the number of MLs is the number of orientations that that orbital can take on. Here is where we see that there are 5 D orbitals, right? And these are all 7 of the F orbitals. Okay. When referring to an orbital, usually both the N value and the letter designation for L value are reported. So you'll write something like, I'm talking about quantum number 2, or principal quantum number 2, and I'm talking about the S orbital there. So the L value is 0. Or I'm talking about principal quantum number 3, N equals 3. And I'm talking about when L is equal to 1, and I'm talking about the P orbital. In the case of the hydrogen atom, energies of all orbitals with the same N are the same. This is called a degeneracy, and the energy levels with the same principal quantum numbers, N, are all called degenerate energy levels. However, in atoms with more than one electron, this degeneracy is eliminated by electron-electron interactions. Orbitals that belong to different subshells have different energies. Orbitals within the same subshell are still degenerate and have the same energy. Okay. Pairing electrons in the same orbital requires energy because the electrons repel one another. So here we can see that as energy goes up, and we start to add on electrons, we get different energy levels. So first we're going to fill this 1s shell, then we're going to fill the 2s shell, then we're going to fill the 2p shell, okay? But because pairing them off requires energy, first we're going to put one electron here, one electron here, one electron here. Then we start pairing them off because each one of these orbitals is going to be able to hold 2 electrons. We'll talk a little bit more about that in just a second. And what this leads us to is our fourth and final quantum number, the spin quantum number. So the first 3 quantum numbers, N, L, and ML, define the region of space where an electron is most likely located. The electron spin is a different kind of property. Electron spin describes an intrinsic electron rotation or spinning. An electron can only spin in one of 2 quantized states. So, the book makes this statement, and I do have to mention that it's actually pretty much wrong. The electron isn't really spinning. What's really happening is that this principal quantum number is existing. It does work just like this. But what it's really trying to get at is that electrons have a directional vector that's associated with magnetism. Spin is to magnetism the same as electricity, or as charge is to electricity. It's the smallest unit of magnetism. So that's just a little extra note for you guys. The spin quantum number, ms, describes the 2 possible states. So you can have plus 1/2 or you can have negative 1/2. And the basic idea being that if I had a vector that was pointing through it, it could be up or it could be down. And traditionally the notion was that this electron was spinning. It's really honestly only been in the last years that this has really been debunked, that they really have this spin to them. But you can kind of think of it like the electron being a little magnet with a north and a south pole that could be oriented in one way or another when you apply an outside electric field. Basically, if I apply this outside magnetic field here, the electron can orient to it or it can orient against it. Okay, so the Pauli exclusion principle. An electron in an atom is completely described by the 4 quantum numbers, N, L, ML, and MS. Wolfgang Pauli, an Austrian physicist, formulated a general principle. This is called the Pauli exclusion principle. That says that no 2 electrons in the same atom can have exactly the same set of all 4 quantum numbers. So by giving all 4 quantum numbers, we can describe exactly which electron we're talking about. Electrons can share the same orbital, but they will wind up having different ms numbers. They'll be arranged opposite one another. Since the spin quantum numbers can only have 2 values, plus or minus 1/2, no more than 2 electrons can occupy the same orbital. So every orbital gets 2 electrons, max. It doesn't have to have 2 electrons. It could have 1 electron in it, but can't fit more than 2. If 2 electrons are located in the same orbital, they must have opposite spins. So here's a nice little table that is summarizing the allowable values for N, L, ML, and MS. All right. So in section 6.4, we're going to derive the predicted ground state electron configurations for some atoms. We're going to identify and explain exceptions to predicted electron configurations for atoms and ions. And we're going to relate electron configurations to element classifications in the periodic table. All right, electron configurations. The energy of atomic orbitals increases as the principal quantum number n increases. As the principal quantum number n increases, the size of the orbital increases and the electrons spend more time farther from the nucleus. Thus, the attraction to the nucleus is weaker and the energy associated with the orbital is higher, less stabilized. So, you can kind of almost think about this as like a satellite leaving the Earth, right? You have to put more and more energy into it in order to get the satellite further and further away from the Earth. In any atom with two or more electrons, the repulsions between the electrons makes energies of subshells with different values of I of L differ. The energy of the orbitals increases within a shell in the order of S, which is less than P, which is less than D, which is less than F. Electrons in atoms tend to fill low energy orbitals first. So let's see what we're talking about here. So what they're trying to say is that the first thing we're going to do is we're going to put an electron in the 1s. Then we're going to put a second electron in the 1s. It's going to have a different spin to the first one. Okay. Now this guy's full. The next electron, if we were to add it, we're going to have to go up to the next highest energy level, and we put an electron in there. Then we pair that guy off. The next electron we add would go into this guy. Okay? But because it requires extra energy to pair off electrons, the next electron would go into this guy, and then the next electron into this guy. Then we would pair these off, and then we would move on to 3s, and then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, so on and so forth as we climb all of these different energy values here. The arrangement of electrons in the orbitals of an atom is called the electron configuration of the atom. An electron configuration consists of symbols that contain three pieces of information. First, you're going to have the principal quantum number, or n, the letter that designates the orbital type, and finally a superscript number that designates the number of electrons in that particular subshell. So this is just kind of a way of writing which shell, where all the electrons are inside of an atom. Here's the simplest example of hydrogen. It has one electron in the 1s shell. The Off Bowel Principle. To determine the electron configuration for an atom, we add a number of electrons equal to its atomic number. Beginning with hydrogen and continuing across the periods of the periodic table, we add one electron to the subshell of the lowest available energy. This procedure is called the Off Bowel Principle, from the German word Aufbau, to build up. When writing electron configurations and orbital diagrams, keep in mind the Pauli exclusion principle. So, what is that? That is exactly what I just said with this diagram back here. And this diagram is basically telling you the exact same thing. You're just heading down these little arrows. So first you fill the 1s, then you fill the 2s, then you fill the 2p, then the 3s, then you fill the 3p, then you fill the 4s, then you go back up to the 3d from the 4s, then you fill the 4p, then you fill the 5s, and then you go back to the 4d, then the 5p, then the 6s, and you keep adding it up as you go along. And you can kind of see that in these blocks. It's kind of the way that the whole table is actually set up. So you have your 1s, so that has 2 electrons, so that's going to be the first one is going to be hydrogen, the second one is helium. Then you have your 2s block, and that's going to be lithium and beryllium. Those are where you're going to put your electrons to make those atoms. Then you have your 2p block. Then you have your 3s block. Then you have your 3p block. And then you have your 4s block. And then the weird thing is that this is actually in the 4th period, but it's a 3d block, which is just kind of the way that it works out, honestly. And then you get your 4p block, 5s, 4d, 5p. So when you're doing the electron configuration work, I really suggest you take a look at this table, because it really kind of helps you to make sure that you get it right. Orbital diagrams. So orbital diagrams are pictorial representations of electron configuration. So rather than writing out numbers and letters, we're going to actually show it with little squares where we're writing in these electrons that you usually represent with these like little hooked arrows here. An upward arrow is going to indicate a positive spin, while a downward arrow is going to indicate a negative spin. So let's see here. So if we have helium in its ground state, neutral atom, it has a electron configuration of 1s2. So it's in the principal quantum number. It's in that s orbital. There's 2 of them. And we're going to write that by making a little square that represents that 1s orbital, and then writing 2 electrons in it with opposite spins. Then we're going to have lithium. Its electron configuration is 1s2, 2s1, so it's got 2 electrons in that 1s orbital. It's got 1 electron in that 2s orbital. If we write 2 blocks representing those 2 orbitals, 1s and 2s, we're going to put 2 electrons in that 1s and 1 electron in the 2s. And then beryllium would be our next guy, and you can see now we're pairing off those electrons. As we get into the p block, you can start to see that rule that I talked about before, where rather than immediately pairing off this guy, we're going to put 1 in each one of these orbitals, and it's not until there's 1 electron in all 3 of the p orbitals that we go back and start to pair them off. This is what's known as Hund's rule. Here we can see the examples as we fill out that p orbitals and start pairing them off. Okay, the difference between valence and core electrons. The electrons occupying the orbitals in the outermost shell, the highest value of n for that atom, are called the valence electrons. The electrons that are inside of that outer shell are all the core electrons, so all of the orbitals on the inside of that with n values less than the highest n value for that atom. The core electrons represent a noble gas electron configuration. Okay, so they're going to have an electron configuration that would be the same as one of the noble gases. And the electron configurations can be expressed in an abbreviated format by writing the noble gas that matches the core electron configuration along with the valence electron configuration. So let's see what they're talking about here. So if I had an electron So this is the electron configuration for sodium here. Then you can see the beginning of this, all its core electrons, the ones that don't have the highest principal number, are the same as the electron configuration for neon. So I will abbreviate it by replacing this whole first part with neon, and then only writing out the valence portion after it. Here's some more examples using various different compounds, and this abbreviation using the noble gas. Here is a very convenient table that is going to help you to do that, where basically what it has here is just the valence electron configuration for each of these guys. So what you would do is say I want to do, calcium here. That's 4s2. I go back all the way over here to this ideal gas that precedes it here of argon. And I say the electron configuration for calcium is argon 4s2. Okay. For strontium, it would be krypton 5s2. And doing that, you can kind of really quickly get from this table the proper electron configuration. Okay. There are some rules about the D subshells that are a little inconvenient for us. So beginning with the transition metal scandium, atomic number 21, additional electrons are added successively to the 3D subshells. These subshells are filled to capacity with 10 electrons. For L equal to 2, there are L times 2, or 2 times L plus 1, 5 values of ML. 5D orbitals have a combined capacity of 10 electrons. After the 3D subshell is filled, the electrons are next added to the 4p subshell. So like we talked about before, it doesn't exactly make sense, but it's the way that it plays out. For the two periods of inner transition metals, lanthanum through lutetium, and actinium through lawrencium, electrons are added to the F subshell. This is where L is equal to 3. There are 7 of them, 7 values of ML, and the 7 F orbitals have a combined capacity of 14 electrons. Okay, here's where we're really getting into the exceptions though. There are some exceptions to the order of filling subshells. There is stability associated with half-filled or fully filled D subshell. An electron shifts from the 4s into the 3D subshell to achieve this stability. And here are some of our examples here. So, we would expect that copper would be 4s2, 3d9. Makes sense when we're filling it in. But in effect, it actually wants to fill this D subshell here. So one of the electrons is not in the 4s, it's actually in that 3d10. Same for chromium. We would expect it to be 4s2, 3d4, but in actuality, it's 4s1 to 3d5. I point these out to you, but I'm actually not planning on asking you any kind of gotcha questions where this is really going to play into it. I try and make these questions pretty straightforward. Okay, electron configurations in the periodic table. The periodic table arranges atoms so that elements with the same chemical and physical properties are in the same group. Elements in the same group have similar valence electron configurations. Valence electrons play the most important role in chemical reactions. This describes why elements in the same group have similar chemical activity. Makes sense? Their electrons are arranged in the same way. They behave the same way. Main group elements or representative elements are those in which the last electron added enters into an s or a p orbital in the outermost shell. The valence electrons for main group elements are those with the highest n level. So here's an example. We have gallium. Gallium has 3 valence electrons, the 4s2 and the 4p1. And a completely filled 3D orbital counts as the core, not valence. Okay? So it's the ones with the highest n levels. It's not always necessarily just the ones that we've written the furthest to the right. Transition elements or transition metals, are metallic elements in which the last electrons added enters a d orbital. The valence electrons, those added after the last noble gas configuration in these elements, include the ns and n-1 d electrons. So here you can see that when we don't have those p orbitals, okay, we consider the 4s and the 3d3 for those transition metals as valence electrons. Inner transition elements are metallic elements in which the last electron added occupies an f orbital. The valence electrons, those added after the last noble gas configuration in these elements, include the ns, n-2f, and if present, the n-1 d subshells. So here we can see that we're going to include both this for promethium. We're going to include both the 6s and the f. Whoops. And the f subshell as being valence. So far we've been talking about neutral atoms. How are we going to handle this for ions? If we recall, ions are formed when atoms gain or lose electrons. A cation, positively charged ion, forms when one or more electrons are removed from an atom. So for main group elements, the electrons that were added last are the first electrons to be removed. For transition metals and inner transition metals, the highest ns electrons are lost first, then the n-1d or the n-2f electrons are removed. So the first we're going to take off an s electron for the transition metals. An anion, negatively charged ion, forms when one or more electrons are added to a parent atom. Electrons are added in the order predicted by the Off Bowel Principle. So let's see here if we can predict the electron configurations for these guys here. What is the electron configuration of these various different ions? So let's start off by writing out the electron configuration for sodium. We saw that before. If it loses an electron, this is a main group guy, it's going to come off of this 3s1, the last electron that was added to it to make this configuration, and we wind up getting this 1s2, 2s2, 2p6 configuration. Phosphorus is another main group one. If it loses 3 electrons, it gains 3 electrons. It's going to go into this 3p orbital right here, and we wind up with having 3p6 here to indicate the 3 gained electrons. Aluminum, if it goes and loses 2 electrons, it's going to come out. Again, this is main group. It's going to first lose this 3p, then it's going to lose a 3s. We wind up getting this electron configuration here. Iron, now we're into our transition metals, okay? If iron loses 2 electrons, and since it's a transition metal, they are removed from the 4s orbital first. So we're going to go to this highest s orbital, and we're going to take those 2 electrons from it, and it's going to keep its d orbitals. For Sm, we have a very long, complicated electron configuration here, but we're not going to get too freaked out about that. If it loses 3 electrons, the first 2 will be lost from the 6s orbital, right? So it's following the same rule up here, where you're going to highest n and losing the s orbital first, but we still need to lose one more, and that orbital is going to come from its highest f orbitals. And we wind up getting this electron configuration here. So first you get rid of that 6s, then you start stealing from the f orbital there. Section 6.5. We're going to describe and explain the observed trends in atomic size, ionization energy, and electron affinity of the elements. So many properties of elements vary periodically as electronic structure of the elements change. We've seen this from chapter 2, and we kind of reiterated it in the last chapter. These properties govern the chemical behavior of the elements. These periodic properties include size, the radius of the atoms, the ionization energies, and the electron affinities. So let's get into what some of these properties are of atoms and how they change across the periodic table. The first one we'll talk about is the covalent radius. This is 1/2 the distance between the nuclei of any two identical atoms when they are joined by a covalent bond. What happens as you move down the group within a periodic table, we're going to get a higher and higher quantum number n. This means that the electrons are added further and further away from the nucleus, and that causes an increase in the size of the covalent radius. This is due to something called the effect of nuclear charge. This is the pull exerted on a specific electron by the nucleus when you take into account the electron repulsion effects. It's these electron repulsion effects that make it so that the electrons have different distances from the nuclei, and they're not all just circling the nucleus at the same distance. In our simplest case, hydrogen, there's only one electron, so the nuclear charge Z and the effective nuclear charge are equal. For all other atoms, the electron of interest are partially shielded from the pull of the nucleus by the other electrons present. So core electrons are providing the most of the shielding. So when you wind up So while electrons in the same valence shell do not block the nuclear attractions experienced by others as efficiently. So it's the core electrons that are pushing out, and the valence electrons in this case. Each time we move from one element to the next across the periodic table, Z increases by 1, but the shielding increases only slightly. That's because the electrons are being added only to the valence shell. The effective Z value increases as we move left to right across the period. Here we have an image of the atomic radius, covalent radius, and you can see it's measured as the distance from the center of this nucleus to the center of that nucleus. And here we have a nice picture that's going to show us the atomic radius of all of the elements in our periodic table. Here we have graphed out all of the various radii, and we can see that we see a general downward trend as we move left to right across the period, and then every time we move up a group we have a nice big jump up, and then back down, up, and then over. Ionic radius is analogous to covalent radius, but this is when we're having an ion, okay? And it's not measured as the distance between two ions either. And basically what happens is if you started with the covalent radius, a cation always has fewer electrons, but the same number of protons pulling on all those electrons. As the electrons are removed from the outer valence shell, the remaining electrons experience a greater effective pull, and charges are drawn even closer to the nucleus. So for this reason, a cation is always smaller than the atoms from which it is derived. An anion always has more electrons and the same number of protons. This results in greater repulsion among the electrons and decreases the effective Z value. This causes the valence electrons to be farther from the nucleus. And for this reason, an anion is always going to be larger. And here we can see some examples with aluminum having quite a bit smaller radius. When you take away 3 electrons, you add 2 electrons to sulfur, and the atomic radius increases quite a bit. So isoelectronic is a term that describes ions or neutral atoms that all have the same electron configuration. So you can imagine that if sodium typically has 1 more electron than neon, you take an electron away, you make a sodium plus ion, and it will have the same electron configuration as neon. As far as the radius goes, the greater the nuclear charge, the smaller the radius in a series of isoelectronic ions and atoms. So when we make them all isoelectronic with them, the only thing that determines their radii is going to be the size of the nucleus, how many protons they have pulling those electrons closer and closer. So here aluminum would be the smallest, with the largest being nitrogen 3-. Ionization energy. This is the energy required to remove the most easily removable electron from a neutral ion or a neutral atom in the gaseous state while it's in its ground state. And so the first electron that we remove is called the first ionization energy. If we take the resulting cation from that and remove another electron, that's the second ionization energy. And if we did it again, that would be the third ionization energy. As we do that and we do more and more ionizations, it becomes more and more difficult to remove an electron. So every time you remove one, it holds each electron it has a little bit closer. Likewise, removing an electron from a cation with a higher positive charge is more difficult than removing an electron from an ion with a lower charge. And this means that successive ionization energies for an element are always going to increase. The second ionization energy will be higher than, say, the first ionization energy. There's some variations in the ionization energies. Energy is always required to remove electrons from the atoms and ions, so the ionization processes are always endothermic, and the ionization energy values are always going to be positive. What happens is as the size of the atomic radius increases of the atom, the ionization energy decreases. The electrons are being held further away from the nucleus. They're easier to knock one off. Periodically, you're going to see the first ionizations decrease as you move down a group, but increase as you move across a period. Here we can picture that trend. It's always going up as we move across the periodic table, and you'll note that we already know that the ones that are down here at the bottom, lithium, sodium, potassium, rubidium, these are all the ones that we're going to expect to form a +1 ion. And so they have low ionization energies, so it doesn't take a lot of energy to put them into that state. That's why we expect them to do that. Up here we have helium, neon, argon. These are the ones that we would expect to not ever form ions because they have very high ionization energies. And then one like fluorine here, you can see he doesn't want to give up his ions. And we're going to see a reverse trend with another property where fluorine actually wants to take on an electron. Here we have a periodic table showing us all of the ionization energies for all of our elements. There is some deviations in the trends of ionization energies, and this is due to the electron configuration. So if we look at beryllium and boron, the electron that we're going to remove during the ionization of beryllium is an s electron, but for boron it's a p electron. Since the energy of the subshell increases as L increases, this means that An s electron is going to be harder to remove from an atom than a p electron in the same shell. So even though we would predict that beryllium would have a lower ionization energy than boron, because we're removing that electron from the s orbital, it's actually a little bit higher than it should be. Here's an example with oxygen and nitrogen. When we remove one electron from oxygen, we eliminate the electron repulsion caused by pairing the electrons in the 2p orbital. So it actually has a lower ionization energy. Because we're removing this instability of having to pair off electrons, it wants to do that. At some point, there is always a large increase in the successive ionization for an element. This large increase corresponds to the removal of a core electron. These are harder to remove than your valence electrons. An example here is that scandium and gallium both have 3 valence electrons. There's a large increase in the ionization energy that occurs after the 3rd ionization energy. So it'll give up those 3 valence electrons, but it doesn't want to give up that 4th core electron. And here we have a table with some common elements and their successive ionization energies. You can see that there is a steady increase as you move to higher and higher ionization energies. Electron affinity. So electron affinity is pretty much the opposite of the ionization energy. Here we're looking at the energy that happens when we add an electron to a neutral species in the gas state. Unlike ionization energies, this process can be either endothermic or exothermic depending on the element. For some elements, energy is released when the gaseous atom accepts an electron, and that results in a negative electron affinity energy. And for other elements, energy is required, and we have a positive electron affinity energy. It becomes easier to add an electron as the effective nuclear charge of the atoms increases. Electron affinities become more negative across a period. There's some deviations from this trend. And more negative here means actually energy is being released, which would mean that would be the spontaneous direction for this. So when they say the electron affinities become more negative, that means it's more likely to happen. There are some deviations. For the noble gases, they have completely filled shells, and so the incoming electron has to be added to a higher principal quantum number, and so they actually have very low electron affinities because they don't want to do that. For group 2, they have the filled NS shell, and so the next one would have to go into a higher energy NP shell, so they have lower electron affinities. And the same for group 15. Once you have to start pairing off the electrons in those P shells. Here is a table showing electron affinity. We can see it for all of our main group elements here. We can see that some of the higher values are going to be fluorine and chlorine, oxygen, sulfur, and we know these to be atoms that want to form negative charges. So they have these very negative electron affinities.